Good afternoon, each and everybody of you joining us today. My name is Namir Amsu, member of Timber Design Society Management Committee. We welcome TDS and CSOC members joining us online today. TDS warmly welcomes new members to join the society. You can apply online and complete the membership form on www.timberdesign.org.nz. It's very simple, straightforward. TDS will upload all previous and next recordings to its home page in the next few days. So stay tuned for that. TDS is also pleased to announce its next confirmed webinar series, the fourth in series on the 1st of July by Lisa to talk on an introduction to mass timber, post and beam structures. And then the fifth in series on 12th August by Andrew Damba to present a Kiwi in Canada, mass timber case studies and timber design learning. And then the sixth in series on the 2nd of September by Ashkan Hashimi to speak on seismic resilience, resilient mass timber structures, the role of the resilient connections. We also have near confirmed in October and November, and we are still looking for December. So if you are interested, just come back to us and we will be very happy to book you in for the last month, and then we'll look forward for 2022. So stay tuned for TDS future webinars and forthcoming events. Today, we have TDS third webinar series in 2021 by Justin Brown, a PhD candidate at the University of Canterbury, talking about timber connections with engineered wood screws. Few housekeeping here today. Justin will talk for 45 minutes, then we'll have questions and answers from the audience, and around for 15 minutes before the hour when we close and everybody returns back to work. This presentation, as I said, is recorded and will be kindly posted and made available by Engineering New Zealand and TDS very soon. A little bit about Justin Brown. He's a PhD candidate at the University of Canterbury, working under the primary supervision of Associate Professor Mingao Li. His research is focused on the performance of CLT core wall systems and CLT connections. In this regard, Justin has researched the seismic performance and design of CLT connections with self-tapping screws. Before starting his PhD in 2017, Justin worked on several multi-story timber buildings across North America as a design engineer at Structure Craft Builders in Vancouver, Canada. He is also currently a co-editor of the New Zealand Timber Design Society Journal. Thank you very much once again for joining us today, and please allow me to welcome Justin Brown. Thank you very much. Justin.
Thank you very much for the introduction, Namir. It's really my pleasure to be here today to present on the topic of timber connections with engineered wood screws. So I want to thank you all for joining in. And I hope by the end of this presentation you can have some insights or new ideas on how you can approach your next project with timber. As Ming-Hao mentioned, as Namir mentioned, my senior supervisor is Ming-Hao at the University of Canterbury. And as part of our research, we looked at engineered wood screw connections, primarily with cross-laminated timber. And the photo in the background is one of our experimental tests where you can see many fully threaded screws used to connect two CLT shear walls together. So in today's presentation, I'd like to start by just describing what an engineered wood screw really is. I'd like to compare this to other products that you may see in New Zealand and our New Zealand Timber Design Standard. Then I'd like to focus on and highlight just some applications of engineered wood screws schematically, showing you some possibilities to implement them. Then we'll get into the design of screws, giving you a broad overview of how you can approach this connection problem. And then finally, I'll give some experimental comparisons, which is some insights from our research here at the University of Canterbury that you can keep in mind for your next project. So screws in general can really be incorporated in three broad terms. In NZS 3603, our timber design standard, we have gauge screws, also referred to as wood screws in this design standard, and coach screws, which are similar to a bolt with a threaded end. We also have now in New Zealand engineered wood screws, which are also referred to as self-tapping screws. And all of these screws have a common terminology to them, and that's what I would like to start with so that we all understand certain components when I'm going through the presentation today. So first of all, starting at the top, we have the screw head, which is where we attach the driver to turn the screw into the timber. Then if we look at this partially threaded screw, we have the screw shank, which is the smooth section of the screw. Followed by that shank, we have the shank cutter, which is specifically designed to drill a hole slightly larger than the shank and help reduce the installation torques required to drive these long screws into our timber members. Then both screws, fully threaded or partially threaded, will have its core or root diameter, which is also shown as D subscript R in this image here on the right. Followed by that, we have the threads of the screws, which is generally how we define the size of the screw as the outer diameter D. The distance between the screw threads is called the pitch. And then finally, at the bottom of the screw, we have the self-tapping tip, which is why these products are also referred to as self-tapping screws. So these terms I'll use throughout the presentation today. First, gauge screws. So these are the screws that we can find in our 3603 design standard. These are generally referred to as size from 4G to 14G, 14 gauge in size. These are 2.7 millimeters in diameter to 6.3 millimeters in diameter. They come in a variety of forms that can be used for different applications, such as decking screws, for example. And they also have many different coatings on them to allow for application in different environments. Some screws also have a T17 tip, you'll see, and this refers to the cutting tip to allow for further ease of installation. These gauge screws are generally less than 120 millimeters in length and also have brittle failure, which I'd like to differentiate between more coach screws and engineered wood screws. Now, for the next few minutes, I'd like to just compare a coach screw to an engineered wood screw, going through all the different components of a screw that I just mentioned. So first of all, starting at the top, we have the head. A coach screw is generally a hexagonal head, whereas an engineered wood screw has many different head types, which gives you some flexibility in design. The outer diameter of coach screws is on the range of 6 to 20 millimeters, whereas an engineered wood screw is smaller on the range of 2.5 to 14 millimeters. And so there is a difference in size in this. The root diameter of a coach screw is slightly larger as a ratio of the outer diameter than an engineered wood screw. And what this means is that an engineered wood screw has more thread area in contact with the timber, and that helps with its withdrawal capacity, which I will discuss next. The screw length is up to approximately 200 millimeters for coach screws, whereas an engineered wood screw can have a length up to 1.5 meters. Very long compared to a coach screw, which allows you to connect a much larger engineered timber members together. The thread length of a coach screw is, depending on the size, it will become partially threaded and usually 60% of the length. Whereas for an engineered wood screw, as I showed in the previous image, it can be partially or fully threaded, which also is used for different application. When we look at the pitch on diameter ratio, this is slightly larger for an engineered wood screw, and this means that there is more timber between each thread, which again helps with the overall withdrawal capacity. On that similar note, the thread angle is much steeper on an engineered wood screw, generally 40 degrees, and this means that there will be less local timber damage on installation as well, again helping with the capacity. And finally, the strength of these screws. Coach screws are generally around 400 MPa, whereas an engineered screw is around 1000 MPa. So a significantly higher steel strength is used in these engineered wood screws, which gives them increased connection capacity. So in summary, when we compare an engineered wood screw to a coach screw or to a gauge screw, they really are a different product. Gauge screws and coach screws can be used and have a strong application in many of our timber buildings. What I want to focus on today is where we can look at using engineered wood screws and where they are a different product and it can provide different advantages. So here is a visual comparison of what I just described, a coach screw to an engineered wood screw, where you can see looking at the head to the shank cutter, which will be there for partially threaded engineered wood screws, to the thread, and finally the screw tip. They are really a different product, specifically engineered for different reasons. Now focusing on engineered wood screws, which I will do for the remainder of this presentation. As I previously mentioned, they can be broadly placed into two categories, fully threaded or partially threaded. Fully threaded screws are used to generate the withdrawal capacity along the axis of the screw. And these can also provide a very high strength and stiff connection. They're also used in reinforcement applications very commonly. A partially threaded screw, on the other hand, is generally used to pull members together, and they're used in scenarios where the screw is under lateral loading and not under axial loading. Focusing on the screw head types, there are many screw head types. I'll just focus on the three main ones that you'll find with engineered wood screws. We have countersunk head, which can provide a flush surface finish to either steel or wood, and these are used in steel to wood or wood to wood connections. We also have a washer head screw, which is used to provide a high clamping action. The head of the screw is really like a large washer that can then clamp two pieces of steel to wood to wood together. So the washer head screw head diameter is significantly larger than a countersunk head screw. The smallest screw head diameter that you will be able to get is a cylinder head screw. And these are specifically made as small as possible to just fit the driver that you will use to turn it into the wood, so that we can actually bury the head of the screw into the wood. And these types of screw heads are used in applications for wood-to-wood connections. As I previously mentioned, there really are many different screw head types that are now becoming available. Different suppliers have their own unique head finishes to help provide different architectural looks as desired. Looking at the bottom of the screw, there are also many different screw tip types that you'll find if you're looking at different suppliers. They're all generally done to provide ease of installation. They also are meant to provide a self-tapping function, to say that they do not require pre-drilling. However, in New Zealand species, which are generally our radiata pine or Douglas fir, is of much higher density than, let's say, European softwoods, for example. Self-tapping may not always work and pre-drilling may be required. And I'll speak about this a little bit later in the presentation. The tip is also designed to reduce splitting on insertion into the timber. And it's also designed to reduce the installation torques. You can imagine some of these engineered wood screws are up to 1 meter long. That frictional area becomes quite large as it's going into the timber, which can make it quite difficult to actually drive in. The tip can also influence the withdrawal capacity of a fastener, and for this I recommend you look at the specific supplier documents, and I will get into that later on in the design. So now I'd like to spend a few minutes just to give you a general overview of how we can apply these screws in typical connections in a timber building. First of all, as a reinforcing element, this is a very common way to use engineered wood screws. This was also our first webinar series given by Daniel Moroder. So I'll just quickly overview this section. Engineered wood screws can be used to provide cross-section reinforcement to prevent tension perpendicular to grain splitting. They can provide notch reinforcement, as shown here, hole reinforcement, and also bearing reinforcement. So in all of these applications, you can see that we are using a fully threaded screw and even most generally a cylinder head. They can also reinforce connections to prevent splitting along a dowel group line. And they can also provide shear reinforcement to actually increase the net shear capacity of a section. So for more information on this topic, I'd recommend that you look at the NZ Wood Design Guide that has been recently published, authored by Daniel Moroder and Tobias Smith at PTL Structural Consultants. And you can also refer to our first webinar, as I previously mentioned. Now, how can we use these engineered wood screws in connections? Floor-to-floor details is a very common way to employ these. First of all, before I get into more of these images, I'd like to mention that the arrows indicate the direction of loading. So if we look at X's, our crosshairs, and our dots, that can be load into and out of the page, and our arrows are loads across the page. So one very common methodology would be to install screws 90 degree at a lap joint, here shown with CLT, to provide an efficient shear transfer method. However, we could also look at this same connection but use incline screws. We know that, and I'll tell you later, that an incline screw can provide increased strength and stiffness for a connection, and that may be desired. We also may look at using a combination of 90-degree screws and incline screws for the exact same joint. And the purpose of this may be to provide increased displacement capacity, especially under seismic loading. We may use these screws in floor-to-beam details to provide a shear transfer into and out of the page, or also on the scenario of a wind uplift case where we need to clamp the panel to the beam below. And if we are looking to clamp those together, we might use a washer head screw to provide support with the CLT and have the threads inserted into the glulam beam below. We could also use this in a steel to floor connection. It doesn't always have to be a wood beam. So here's a steel side plate where we again can achieve the same loading, but with this time we may use a partially threaded screw, and it may have a hexagonal head so that we can get a sufficient bearing on the steel surface. They're also commonly employed in wall-to-floor details. Here I've shown a steel side plate with partially threaded screws that can provide a shear transfer into and out of the page, or also be used as a tension strap under the cases of hold down forces at the corners of walls. And this can also be used to connect floors to walls below. We may not want that steel plate on the end, and if that's the case, we could also use incline screws to achieve the same connection and resolve this detail, but in a different manner. So in this case, we may use partially threaded or fully threaded screws to provide a sufficient connection from the wall to the floor below. We may want to connect two perpendicular walls together, and we could achieve this again with partially threaded or fully threaded screws. These screws could be installed at 90 degrees or also at inclined to the timber grain if you want to again achieve higher strength or stiffness. We can also install this with the steel side plate again between two wall panels at an in-plane joint. And again, with a steel side plate, we would look at a partially threaded screw and possibly a countersunk or hexagonal head. We may need to connect two beams together. In this case, I'm showing an internal steel plate with a partially threaded screw connecting it to the main beam. But instead of installing those screws at 90 degrees, we may look to install them inclined so that we can take advantage of the withdrawal capacity of the engineered wood screw. And so in this case, we may actually look at a fully threaded screw to achieve perhaps a more efficient connection detail. So I hope that gave you a quick snapshot of where you could use these screws on your next timber project. And now I'd like to actually discuss how we could design those screws. So to design these screws, currently they are not listed in the NZS 3603. So at the moment you will be required to refer to the specific supplier European technical approval document. These documents are available through supplier websites, and they are freely available and contain lots of information on the design of their product. Within that ETA, you will see that you find and require the embedment strength, the yield moment, the withdrawal parameter, the head pull-through parameter, and the tensile capacity of the screw. From your end as a designer, you will have to understand what is the timber density that you are dealing with. For radiata pine in New Zealand, that can often be 440 kilogram per meter cubed. And then we need to understand the angle between the screw axis and the timber grain direction, and the angle between the screw axis and the direction of the load. So now I'll take a minute to describe these 5 different key components that you'll find from the European technical approval. First of all, the embedment strength. Embedment strength is really a bearing pressure of the screw or a dowel as a reaction force against the timber. So this bearing pressure acts perpendicular to the axis of the screw. And in this photo here, I'm showing some testing that we did at the university with a smooth dowel being pushed into a CLT piece of wood. Here we can see the representative load displacement curve, and that embedment strength is determined by offsetting the elastic portion of the curve with this red line and determining the point of intersection. We then take that force and divide it by the length of the screw and the diameter of the screw. And that gives you your embedment strength, which is a property for design. The next value is the yield moment. That is generally given as an equation or tabular value in the ETA. And here I again show some testing from the university where we are determining the yield moment of a smooth dowel. So it's literally a function of the steel property, which gives us this yield moment. Perhaps the most unique parameter of an engineered wood screw compared to coach screws or gauge screws is their withdrawal capacity. And so that's shown here on the left, where we can see a fully threaded screw being lifted out of the wood, or a partially threaded screw being lifted out of the timber member. This is generally provided as an equation or tabular value in the ETA, and it's usually a function of the diameter of the screw. So that will be what you see in the table. In these photos here on the right, I show some of our experimental testing in the lab, where you can see we pulled screws out of this CLT member installed at 90 degrees to the timber grain. Here you can see the associated failure mode at the timber surface, which is timber splitting. We also installed these screws at 60 degrees to the timber axis, which would have a different associated withdrawal capacity. And finally, we installed them parallel to the timber fibers. And here you can see there's a distinctly different failure mode between this 90-degree test and this parallel to the grain test. This is actually a local conical shear failure, as the timber fibers around the area of the screw thread are actually pulled out of the timber member. Currently, as design standards may not allow screws to be installed parallel to the screw thread, and ETAs provide specific guidance on this if it is allowed. I will say it should be approached with caution, as there is some long-term duration effects and moisture considerations, which lead you to these conservative strength reduction factors for the screws installed at this angle. Another parameter is the head pull-through parameter. This is generally used in the case of washer head screws, and it's really a function of the surface area underneath the head of the screw. And so here in the bottom, I show a photo from work by Fitzgerald et al., where you can see this bearing pressure being developed underneath the surface area of the washer head screw as it's being pulled through the member. So that will generally be a tabular value in your ETA as well. The final value that you'll look for in the ETA is the tensile capacity of the screw. Here's a testing photo from the lab again, where you can see part of the screw is actually stayed in the timber. It has snapped right at the surface, and here's the other end shown here in the person's hand. So this tensile capacity is generally a tabular value given in the ETA, and it's usually compared against the withdrawal capacity in your design. And this will be something that I will discuss more in the upcoming slides. So now that we understand the key parameters that we're required to look at engineered wood screws, I'll now look at how we can actually determine their load carrying capacity first in shear, so when they're laterally loaded, and then second I'll look at when they're loaded in withdrawal. When we have a screw that's loaded in shear, there are a certain set of equations that we will refer to from the ETA to determine the capacity of the connection. Those set of equations are referred to as the European yield model, or the Johansen equations. And I won't get into each equation in significant detail, because this will be a future webinar series from the TDS. So I'll just say, please stay tuned to learn more about this topic of the European yield model. It will be an important presentation in the coming months. What I will say is that the failure modes are a function primarily of the embedment failure, as I described before, and the yield moment of the fastener. It's also a function of the thickness of the two members that you are connecting together. So quickly looking at these images, starting at A, we can see that in A and B, we are looking at embedment failure, either in member 1 or in member 2. So the photos here are showing the failed shape of the connection. When we look at failure mode C or D, we are getting into a combined embedment failure and screw yielding failure, especially when we look at D and E. In these cases, we can see that the screw has yielded, and there is also some embedment deformation occurring at the interface of the joint. Finally, if we look at failure mode F, that has a yielding of the screw in both members, 1 and 2, and an embedment failure. That is what these equations allow you to do, is determine which failure mode is likely to occur in your connection. In order to do that, we have the set of 6 equations, which again, I won't get into the details of them, but as a designer, we look at the minimum value, and that is then the design strength or load carrying capacity of our connection. So this portion in blue is really a function of the embedment strength and the yield moment, which I just described in the previous slide. And this section in green is a unique component that we consider for engineered wood screws, which is the rope effect. So now I'll just take a moment to describe what is the rope effect. So if we look at that idealized connection from the previous slides, the rope effect occurs when a connection engages in a small deformation. And as that member is sheared, the screw actually develops a force along its axis, as you can see here in this free body diagram. So that tensile force is developed as the withdrawal capacity of the threads. That tensile force along the angle of the screw can be resolved into a compression component shown in red and a component parallel to the grain shown here. That component shown in red is perpendicular to the shear plane and tends to clamp these two members together. That effect is quite significant, and that is what we actually call the rope effect. So from a designer's point of view, we can basically increase the capacity of a shear connection to consider not only the embedment and the yield moment of the fastener, but also the withdrawal capacity, because it is clamping the members together. So that rope effect is usually determined as the minimum of the withdrawal capacity divided by 4, or the shear capacity. So this is an important parameter and can effectively double your load carrying capacity in shear if it is present. Now, looking at the design of engineered wood screws as they're loaded in withdrawal. This is a larger image from our previous slides, where I show that the idealized case where a screw is loaded along its axis and pulled out of the timber member in a pure withdrawal scenario. In this case, in order to determine the design strength of this connection with a screw, we would choose the minimum of the withdrawal strength, which is a function of the thread, or the tensile strength, which is a function of the steel capacity. The withdrawal strength will be determined by reading that withdrawal parameter from the European technical approval, multiplying it by the diameter of the screw, the effective insertion length, divided by an angle adjustment. And that equation for the angle adjustment will be unique to the ETA as well. However, in most cases, these screws are not perfectly aligned to the direction of the applied load. And by that, I mean there is an angle between the screw axis and the direction of the load. And that angle here I show as phi. So in order to design these screws loaded in withdrawal, the simplified model that we look at is to consider that withdrawal parameter is developing along the effective length of the member, which creates a withdrawal capacity RA. That withdrawal capacity, which is along the axis of the screw, can be resolved to a component that is parallel to the direction of the applied load. And then, therefore, that is how we actually determine what the withdrawal or the shear capacity of this screw would be in withdrawal. The screws are connected by on both sides, two members, and so to determine the connection capacity, we look at the minimum of member 1 or member 2. If we have screws installed in a cross configuration, which may occur, especially if there's load reversal under seismic loading, the simplified approach would be to say that we could just multiply that capacity by 2, again considering that we choose the minimum of member 1 or member 2, which will be determined based on the effective length of the thread on each side. However, I say this is the simplified model because it doesn't fully capture what is actually occurring at the connection. So now I'll just take a moment to describe what is actually happening and show you what a more detailed model of withdrawal capacity might be for an inclined screw. So if we look at that member 1 now again, in reality, because that screw is not perfectly aligned with the applied shear force, the screw axis is not aligned with the applied shear force shown down here, there is actually a combination of embedment stresses and withdrawal stresses occurring on that screw. And I already described how that withdrawal parameter can be resolved to a withdrawal capacity, RA. But this embedment force is also occurring perpendicular to the screw axis, and that can be resolved into a force RV. So the detailed approach of designing these connections would say that there is actually a withdrawal component and a shear component that is contributing to the connection strength. We can resolve that RA into its force component aligned with the force, as I had shown here. But then there is also this shear component that we should consider, which would then be the sine of the angle. There is also this mu that is included in this term, which is to account for that clamping effect that I previously described, which is the rope effect. So as with the previous model, ultimately we need to determine the capacity of member 1 and member 2, and the minimum value will be what governs your connection. Because this screw is loaded in a shear tension manner, we call this a shear tension screw. If it is loaded in the other direction, we would call it a shear compression screw. If you can see, I've rotated it to be aligned differently between member 1 and member 2. In this case, if we examine it in more detail, we would actually find that there is a zero stress area at the interface between member 1 and member 2. That zero stress area, it physically has a physical meaning in that because the screw is installed in the opposite direction, there is a prying effect that is actually occurring at the interface of the joint. That prying effect provides a tendency to split the timber, and therefore we take a certain length, x1, as a zero stress area. It has no contribution to the withdrawal strength or the embedment strength. To define that length, we have this equation here, which has been provided recently by Johansen et al. And used in our more detailed models that I'm describing now. So in this case, we do not have a friction term because, again, instead of clamping the members together, the force components shown here tend to split the member apart. Again, as with the other models I have shown, we always choose the minimum of member 1 or member 2. So if we are to design a X configuration or a cross configuration of these screws, the detailed approach, similar to the simplified approach, is to just simply add them up. A shear tension screw and a shear compression screw. That equations are just simply provided here. And you'll notice that because we have these screws installed in cross configuration, that friction term has gone away. They cancel each other out and we lose that tendency to clamp the two members together. If we decide to install a combination of cross configuration screws and now screws installed at 90 degrees, the method that we've proposed in recent work has been just simply to add them all up as well. So we would have a shear tension screw, a shear compression screw, and just a shear screw, which is your 90-degree screw. This is more of a simplified approach, but has been shown to provide sufficient accuracy at this time. So some final considerations for the design of these screws. I've now reviewed how we can design a screw under lateral loads using the European yield model and under withdrawal scenarios where we have to consider the actual withdrawal strength of the screw. My first recommendation is to look at the European technical approval of the screw supplier you are chosen. There are some differences between screw suppliers. However, they may be small. It is important that we understand where they may be coming from, which could be due to different screw tips, a root diameter to outer diameter ratios, etc. I think in New Zealand, pre-drilling is quite commonly required, especially when we start to look at screws 8mm diameter or larger, and especially of lengths greater than 200 millimeters. This helps to reduce the splitting tendency of wood and can also reduce the spacing between the screws, which I will describe in a moment. So on that topic, something that I haven't discussed yet is how we actually install a group of these screws. Everything I've discussed previously has just been around one screw or a short group, but in all of our ETAs and design standards, we will find a minimum spacing. And that minimum spacing between an engineered wood screw is dependent on the loading direction, the timber species, whether or not to be used pre-drilling, and the type of wood product. So quickly, you may see diagrams like this, where if we are loading parallel to the grain of the timber, we have certain spacing requirements. If we're loading perpendicular to the grain of the timber, and axially to the timber. So I'll just say that these minimum spacing requirements are very important, and the idea of them is to reduce the likelihood of a premature brittle failure mechanism. The European yield model in particular is derived based on those 6 equations which focus on a non-brittle failure mode. However, we could have tension perpendicular to grain, for example, which is brittle failure modes, or row shear failure modes as a group of fasteners, and this minimum spacing is very important to ensure that that does not occur. Okay, now for the last 5 minutes, I would just like to give some insights from our experimental testing here at the University of Canterbury. As a designer, you may be looking for certain performance indicators, and I hope through these next slides I can illustrate that the way we install the screw will significantly affect not only the strength, but also the stiffness of the connection, the displacement of the capacity of the connection, which could be important for cyclic or seismic loading, and the failure mechanism. So on the right side, for the remainder of our slides, I have an image of these 6 different installation methods that I just described the design of, and I would like to show you some force displacement curves so that you can have a feeling for what their differences might be. So first of all, looking at screws installed 90 degrees to the timber grain. We would describe these screws as having a relatively lower stiffness, but a larger displacement capacity. If we were to design those screws, the characteristic capacity I would receive is somewhere down here. However, this shaded area in blue indicates that significant clamping effect that can occur as the deformation of the connection increases. Those screws become more aligned with the direction of the load, and we get an increased clamping effect. So it really is quite significant. If we were to install a very long cross configuration screws, we might define these as having we can see they have a much higher stiffness, connection stiffness shown in gray. However, in this test, we had a brittle screw tensile failure. So instead of a withdrawal failure mechanism, steel failure was the minimum value, and we therefore lost the connection load very abruptly, which would not be advantageous, especially in the case of seismic design. To control that failure mechanism, we could reduce the length of the screw, and therefore we are reducing the amount of effective length of thread on each side of the member. By doing this, we can say we have a more gradual failure mechanism, shown here in red, as we see the load dropping off. However, you can also see we have a very similar initial stiffness to that long inclined screw. If we were to install short shear tension screws, and only screws in shear tension, you can see we could reach our highest strength capacity. They have a very high stiffness, but also a gradual failure mechanism, because the governing withdrawal capacity was screw withdrawal failure, not tensile steel failure. So a very important consideration there. Next, if we were to install screws in shear compression, this would be very uncommon to do just on its own. However, just to illustrate, this would provide a much lower strength, a very high displacement capacity, as you can see here, and in fact, no failure around a 40 millimeter connection displacement. So this shows you the difference in load capacity that can happen because of that zero stress area, depending on the installation angle that occurs. Finally, if we install screws in a mixed angle configuration with both 90 and short incline screws, our force displacement curve may look something like this, where we have a nice initial stiffness comparable to our inclined only connections, but we get this more stable post-peak behavior that allows us for an increased displacement capacity, which may be required, especially in seismic loading scenarios. Speaking of seismic loading, I'd like to show you some hysteresis curves from our cyclic testing in the lab. And specifically, I'd like to compare what a cross configuration setup might look like compared to a mixed angle configuration. So shown here below, we can see that our hysteresis curves are here in black as we move that joint back and forth. The one thing I want to highlight is the displacement capacity and the difference in these connections. So in the cyclic loading scenario, we may be limited to only 10 millimeter displacement capacity if we only have short incline screws, as you can see here. However, if we install mixed angle screws, we can significantly increase that displacement capacity, in this particular test, greater than 20 millimeters displacement, because the 90-degree screws are engaging and providing that increased capacity. So from a seismic point of view, if your connection is required to behave in a ductile manner and not to be elastic, this could be something important to consider. Finally, I'd like to just present you with some additional resources. Engineered wood screws is a very large topic. They're one of the most readily used fasteners in mass timber buildings today. And for that, there's a lot of information that you can look at, and free information that I want to show you with. So first of all, this Timber Engineering Principles for Design book is a publication by Professor Blas and Sandhaus, available for free online from KIT Scientific Publishing. There's also an annual timber meeting called the Intermeeting, and there are online proceedings available from that, which can provide you state-of-the-art information on timber connections. Again, as I said, the European technical approvals for each supplier are readily available, which can also give you a lot of fantastic information. And finally, I'd like to mention that a lot of this images were actually taken from MTC Solutions Structural Screw Design Guide, which is a timber screw, engineered wood screw specialist company in Canada. And they have a guide that's also freely available and that I would recommend you look at. Lastly, I'll leave this bibliography here, not to go through, but when you look at the recording later, if you'd like to see more detail on those references, I have them available for you. So thank you very much for listening today. I hope you enjoyed the presentation, and if anything, can better understand now some of the differences between an engineered wood screw, a coach screw, and a gauge screw, and how you may look to implement them on your next project with timber. Thank you very much. I'm happy to take questions now.
Thank you very much, Justin. Very thorough and interesting talk. You've explained or maybe summarized the types of engineered wood screws and also its applications whereabout, and that's really very interesting to hear. We have so far many questions. We'll make a start on the most liked ones. You may like the questions published. We'll start with the first one. This is not a question. Will these slides be available after the session?
Yes, we will be placing them available on our Timber Design Society website. And like Namir mentioned, the recordings will also be available afterwards as well. So please revert to our TDS website.
Okay. Next, how do installers ensure correct edge distance and angle of incline, specifically for inclined screws when 5 millimeter out of place could result in significant reduced in capacity. How do engineers confirm this post installation?
Thank you for the question. I think it's a very topical one that is of concern for a lot of people. What I would recommend is that in these instances, this is where pre-drilling can play an important role. And pre-drilling of your timber members can provide a much better screw alignment on installation on site. So that pre-drilling can actually ideally occur in the fabrication stage, off-site in a controlled environment, and to do that pre-drilling accurately so that we have the correct angle and edge distance, as you mentioned. The screw suppliers also have many guides that you can actually fasten on and then install a pre-drilling hole through it to ensure different angles. These could be single angles, compound angles, and this can really help guide you on the construction site. I will say that is an important reason to pre-drill. If we aren't pre-drilling, especially with longer screws, there could be a tendency for the screw to find its way into the wood, which could change depending on local knots, etc. So this is one reason why I think pre-drilling is very important and is becoming more and more used just to ensure correct installation, more so than even to reduce splitting. Thank you for the question.
Yeah, we have another question saying what type of surface coating is required for screws installed in timber in the outdoor environment?
Yeah, thank you for the question as well. I would refer you to the specific suppliers. For outdoor environments, many suppliers, I would say almost all, will also provide stainless steel screws, which could be required if it's a very intense environment. Most screws will have some type of coating on them, either hot dip galvanized or etc. Some screws also may have, and suppliers may have their own specific coatings that they are offering. Delta Seal is a coating from Spax, which is a product I've worked with that's available here. And that one has been shown through their own testing to be able to handle, highly extreme environments, outdoor environments, and also potentially corrosive environments too, due to treatment. So depends on the supplier, but for sure stainless screws will be available as a first start.
Okay, now we have a question from, it's changing, anonymous now. AL, NZ3603 references gauge screws with their shank diameter, which I believe is true for screws having insufficient difference between the thread and shank diameters. As the current gauge screw in the market have a significant ratio between the thread and shank diameters, is the data in NZS3603 still applicable?
Yeah, I think that's an important question, and what I would refer you to is more or less what you just said, is that these gauge screws are provided in 3603 with their tabular values depending on the joint group. So looking at J4, J5 most commonly. That's what I would still recommend you to use for design. However, when we're looking at these engineered screws, as they are a different product, we need to look at the European technical approval of them, where they will give you specific information on using the outer thread diameter or the inner shank diameter. So it allows you to differentiate between it. So thank you for the question.
Okay, now another question saying, noting design of engineered, it's changing. of engineered wood screws are not covered by 3603. Is the use of engineered wood screws considered an alternative solution as defined by the building code?
Yeah, thank you for this as well. As I mentioned before, my work has primarily been on the research side here in New Zealand, but I am aware that if engineered wood screws are specified in design, this most usually leads to a peer review process through the alternative means. I think it also depends on the situation in which they are used. So if they are used as critical details on the building, then they will more than likely go through this peer review process. But this is, councils are becoming more and more used to this product. And I think as the uptake of them continues to increase in New Zealand, we can start to see more and more availability. So thank you.
Okay. Now, the other question. When would you need a screw 1500 mil long?
Okay, yeah, that's a very long screw. And when I first discussed the applications of engineered wood screws, one of the first topics I showed was the reinforcing application of them, which was the previous webinar by Daniel Moroder. And we now are often fabricating, let's say, glulam beams or rafters and portal frames, where the members can be quite large, larger than 1 meter. And depending on their location, we may need to provide reinforcement, tension perpendicular to grain, or additional shear reinforcement. In these situations, you may need very long screws. 1.5 meters is quite large, but the idea was just to illustrate that they can be significant, and up to 600 millimeter length is very easy to find.
Okay, another question. How does a partially threaded screw perform better under lateral loads compared to a fully threaded screw?
Yeah, a partially threaded screw is often, I wouldn't say it necessarily performs better, it performs slightly differently in that a partially threaded screw, first of all, if the thread is only located on one member, we'll tend to clamp them together, which can help provide that rope effect I was even describing, if you have the washer head side. Whereas a fully threaded screw, if you are looking at them in dowel action, it will not suck the members together because the thread is on both sides. So from a construction point of view, you may not achieve that clamping action on installation. However, once the connection is loaded, you could engage it and then start to clamp it together. So that's just really a difference, and it depends on the detail you're looking for on the job site.
Okay, a question from Oscar saying, when minimum screw embedment requirement cannot be met, what strength reduction method should be used to obtain accurate capacity?
I think that's an important question, and maybe more applicable when you're using smaller timber members. I don't have an answer for you. I'm happy to follow up with you, so feel free to send me an email. I would say that the minimum requirements are there in the ETAs specifically for engineered wood screws, and are important to ensure minimum capacities. So if this is a specific case, you may need to approach it on a case by case and with caution. Thank you.
Okay, now we have a question from Maria Grace from Invercargill City Council. She's saying, would use and correct application of engineered screws on site, normally overseen by engineer, for example, construction monitoring, or would building inspectors ever be involved in checking, fixing patterns, etc.? Thank you.
Yeah, I think it's an important question, and I think it will probably depend on how and change as we start to use them more readily in the market in New Zealand. So in these earlier stages, as they're a more relatively new product, you may see more on-site involvement from the design engineer, possibly working with contractors and inspectors at early stages. And then as it becomes more accepted, this may not be as required, but I think it's a case by case and dependent on the local expertise.
Now, we have another question. I think it's important. How do the ductile screw capacities compare to ductile nail capacities?
Yeah, thank you for the question. Nails can have this ductile performance, especially in light timber frame shear walls, especially with plywood as the sheeting. And I think I would differentiate them because screw diameters are generally significantly larger than nails. And so in that case, they should have a higher lateral load carrying capacity, whereas the nails are often quite slender, which means that they are going to yield quite easily and quite early during loading.
Okay, now we have another question from Chan saying, which of the failure modes within Johansen equation is the preferred mode for a structure that is designed as nominally ductile structure?
Okay, it's a specific question. I think that, yeah, thank you. I think I can start to answer that. It does, what you'll find is that the Johansen equations and the minimum value you get is really a function of the embedment strength and the yield moment of the fastener. And then also when we look at longer fasteners, we start to yield them more easily. If it's a short stocky fastener, you may start to see more embedment failure versus a long slender fastener. We will actually start to bend the fastener more easily. For nominally ductile structures, we aren't relying on significant ductility from the connections. However, in any case, the preferred failure mode in terms of any ductile failure with these engineered wood screws would be to have some yielding occurring of the screw, not just timber embedment crushing. So in that case, I would say from a seismic point of view, we always should be looking towards those later failure modes, D, E, and F as an advantageous approach. Thank you for the question.
Okay, now we have a question from Matt Stewart. For screw spacing in 3603, it lists minimum spacing based on screw diameter. Should outer diameter or root diameter be used in determining this minimum spacing?
Yeah, for 3603, you'll be looking at the gauge screws generally and the coach screws, and that they're generally specified with the outer. With the engineered wood screws, again, I look each ETA, the supplier document, will also have their own spacing requirements, and it generally is a function of the outer screw diameter, which is the outer thread diameter as well. Thank you.
Okay, now, is it fair to say that coach screws are just another form of engineered wood screws? And why the differentiation? And since there are also many subsets of EWS.
Yeah, thank you for the question. I would like to keep them as, I personally think they're quite a different product. The engineered wood screws, they are a huge group of them that I spent the remainder of the presentation to discuss. But at the beginning of the presentation, I tried to differentiate between a coach and engineered wood screw. While a coach screw has a very good application in timber buildings, engineered wood screws have a different application, and I think they are a different product. So thank you for the question.
Yeah, this would be also another interesting question. Could you comment on drilling through structural steel, considering self-drilling metal screws versus pre-drilled holes through the steel for self-drilling timber screws?
Yeah, this is a good question. If we have steel in a connection where we're looking to use engineered wood screws, steel is usually placed on the outside of the member, and it wouldn't generally be in the inside. And in that case, we have the hole large enough such that the thread can pass through, but then the head of the screw and the shank is what is actually connecting the steel plate to this to the engineered wood screw. If we need to actually pass a screw through an internal steel plate, we shouldn't really be looking at engineered wood screws, but rather self-drilling dowels, which is a different product that is available where they actually have a cutting tip on the end of them and then a continuous smooth shank, so that we can ensure that we have the smooth shank engaged with the steel portion. So thank you for the question.
Yeah, maybe at a later stage you may be able to provide typical shear and tension values for these screws into timber. I don't think we have time to demonstrate that.
Well, what I can say, if I can, thank you. It's a good point, and a lot of the screw suppliers actually have readily available design guides that do have your, let's say, preliminary capacity charts to give you an idea on where they would sit. So look for that online, and you can get that information.
Okay. I think we might have the last question. What ratio of screw embedment to the timber thickness would be considered a short versus long scenario, or would it be a set value screw embedment value?
Yeah, thank you. If I understand the question, we're referring to my last slides where I looked at long incline screws and short incline screws to change the failure mode between tensile failure of the steel and withdrawal failure of the threads. In that scenario, in my testing, which was with one product, we generally found if we limited that embedment length to 10 to 12 times the screw diameter, we could prevent steel failure. I will say that there are different withdrawal values for different suppliers, so it's a good idea to take a look at that. But on the range of 10 to D to 12D as the embedment length is a good takeaway number to keep with you. Thank you.
Yeah, I think there are a couple of interesting questions. The first one is saying when the screw is used at 45-degree angle, still can be used its full strength or need to apply strength reduction factor?
If the 5-degree angle, it depends if that angle is between the direction of the screw axis and the load or the grain direction. And what I'll say is that there are reduction factors in the ETAs to give you that guidance. So thank you.
Okay, the very last question. Is there a minimum spacing between the pairs of cross screws?
Yeah, generally from a spacing point of view, we actually look at the, on each member, we look at the centroid of the embedment length. So if there's 100 mil of screw thread on one side, we would then consider the middle point, 50 millimeters, as that location. And we look at the next screw, find the centroid of that embedment length, and ensure that we follow the minimum spacings as specified in the ETA. And most ETAs actually give diagrams to describe what I have just discussed. So thank you for the question.
Yeah, thank you, Justin. I think for other questions, you may be able to go through them, and you are happy to answer them in your own time. And once again, we would like to thank you very much on behalf of the TDS Society in New Zealand. Thank you for your time, and wish you really good luck in your PhD exam, and all the future is yours. And ladies and gentlemen, thank you very much again, and look forward for the next fourth TDS webinar on the 1st of July by Lisa Oliver. Look forward to see you all. Thank you very much. Have a lovely and great day. Bye for now.